Applied mathematics is built on a surprisingly wide range of fundamental areas. Some familiar, others less obvious. Let's go through each branch of applied mathematics. Complex analysis. Complex analysis studies how complex numbers function. Although it's applied in various fields, an interesting tool is conformal mapping, which transforms shapes into other ones without distorting angles. For example, if you're studying heat flow or fluid flow around a strangely shaped object, you can use a conformal map to reshape the domain into a circle, solve the problem there, and then transform the solution back. Ordinary differential equations. Ordinary differential equations, or ODEs, describe how quantities change with respect to a single variable, which is usually time. They are used to study both linear systems, which are solvable analytically, and nonlinear systems like chaos. ODEs are naturally found when modeling just about anything, from planetary motion to population growth. Partial differential equations. Partial differential equations, abbreviated as PDEs, involve functions of several variables and their partial derivatives. They are absolutely essential when modeling distributed systems like heat flow, sound, fluid dynamics, and electromagnetism. In applied math, they can be classified into three types: elliptic, parabolic, and hyperbolic, each one of them with its own behavior and solution techniques. Integral equations. Integral equations are basically equations where an unknown function appears under an integral sign. The techniques used include classification into Fredholm or Volterra types, as well as exploiting properties of kernels. For example, take the Volterra integral equation of the second kind, where the unknown function appears both inside and outside the integral. It models systems with memory, like how a population's current growth depends not just on today's size, but on how it's been growing over time. Perturbation theory and asymptotics. Perturbation theory deals with problems that depend on a small parameter, often denoted as epsilon, where exact solutions are hard or impossible to find. The idea is to start from a simpler, exactly solvable problem, whose solution is A0, and then build corrections step by step. Each AN captures the nth order correction. If epsilon is small, higher order terms get smaller. We even use big O notation to show the size of the remaining error. A classic example would be singularly perturbed differential equations, such as boundary layer problems in fluid mechanics. Calculus of variations. Calculus of variations studies how to find functions that minimize or maximize certain quantities, or maximize certain quantities that are typically expressed as integrals. In applied math, this area leads us to Euler-Lagrange equations, which deal with optimal solutions. The famous Euler-Lagrange equations tell you exactly what condition that optimal function must satisfy. For example, they explain why light follows the path of least time, not just the shortest distance. Special functions. In applied mathematics, special functions are especially important as solutions to differential equations that model physical phenomena, like vibrations, wave propagation, and heat flow. Some examples are Bessel functions, Legendre polynomials, and hypergeometric functions. Bessel functions, for example, naturally appear when modeling the vibration of a drumhead. They capture both the geometry and boundary conditions of the problem. Spectral theory. Spectral theory studies how linear operators can be decomposed in terms of their eigenvalues and eigenfunctions. This area generalized the concept of diagonalizing a matrix into infinite dimensional settings, like as an example, differential and integral operators. It's used in understanding stability, resonance, wave propagation, and signal processing, and many other areas.
Approximation theory. This area studies how functions can be approximated by simpler ones, such as polynomials, splines, or rational functions, and how accurately this can be done. It answers questions like, what's the best way to represent a complex function while having limited data or resources of computing? Approximation theory uses methods like interpolation, least squares fitting, and wavelets. Numerical linear algebra and matrix analysis. The area keeps its focus on developing and understanding algorithms for solving matrix problems, especially to create computer algorithms. Numerical linear algebra and matrix analysis is the basis for almost all of computational science, from simulating different physical systems up to analyzing data. Continuous optimization. Continuous optimization is concerned with finding minimum or maximum values of a function, which is subject to constraints, where the variables vary all the time. It's important in linear and non-linear programming. Linear programming deals with problems with linear objectives and constraints, but non-linear programming with more general and often much more complex cases. Numerical solution of ordinary differential equations. This area studies algorithms for computing approximate solutions to ordinary differential equations, because these often cannot be solved analytically. Take Euler's method, which is often used here to model a step-by-step estimate of how the population evolves over time. Basically speaking, the system gives us reliable results, even if the system behaves chaotically, or if it spans multiple timescales. Numerical solution of partial differential equations. Like the previous area, this one also focuses on computational methods for approximating solutions, but this time to partial differential equations, because they usually cannot be solved exactly. It uses many different types of techniques, but one approach is the finite element method, which breaks the domain into small and flexible pieces and then stitches together local solutions. It's especially useful when the geometry is complex, like when modeling stress in an irregularly shaped bridge. Application of stochastic analysis. Stochastic analysis tries to understand probabilistic behavior over time, and does so by developing simulation methods. So basically, it blends the theory of probability with analysis in order to study how randomness shapes the evolution of a system. If you take stock prices, they clearly don't follow neat curves, but wiggle unpredictably. That behavior is captured using stochastic differential equations. Don't forget that we always attach a PDF file in the description below that summarizes everything we're talking about. Now, here's something you might find very useful when you study it: a PDF editor called UPDF. It might be really annoying to have a PDF file that you can't really do anything with except write on it with probably your really bad handwriting or print the file. But UPDF lets you do much more than that. It's an actually affordable software. It only costs 1/6 of the other one that drains your wallet, and yet just as powerful. It does everything and more to allow you to edit your PDFs. UPDF allows you to edit your PDF files like you'd edit any Word document. Just click on any word and type whatever you want. Edit existing text and add new things.
What if you don't want to keep it as a PDF file? No problem. You can convert it into a Word document and keep the formatting, or even compress it if it's too big. And like all proper modern programs, UPDF has AI support. You can ask it to summarize the contents of your file, ask questions if you have any, or even compare different files. And you would think that this is all you need, right? No, there's more. UPDF is not only limited to one device at a time, but can be used on 4 devices, no matter whether they're Windows, Mac, iOS, or Android. Since most of us switch between laptops, tablets, phones, you name it, it is super useful.
You can use UPDF for free, but it'll leave watermarks and annoying things like that. But I have good news for you. You can upgrade to UPDF 2.0 using our discount in the link in the description. UPDF 2.0 gives you even more features, where you can create PDFs, annotate, highlight, and so on. Make sure to check it out using the link in the description below or in the pinned comment in the comment section. Inverse problems. Inverse problems involve determining hidden causes from observed effects. For example, reconstructing an image from tomography data, or identifying material properties from surface measurements. Mathematically speaking, inverse problems require inferring unknown inputs to a model from its outputs. Computational science. Computational science is the study of using computers to solve mathematical models of complex physical, biological, engineered systems, and so on. Pretty straightforward. Data mining and analysis. As you might expect from the name, data mining and analysis focus on the extraction of patterns and other useful information from large or complex datasets. This involves statistical techniques, machine learning algorithms, and mathematical modeling in order to interpret, classify, or predict the behavior of the data. Network analysis. Network analysis studies systems of interconnected components. It models them as graphs of nodes and edges. One really important idea in network analysis is centrality, which is figuring out which nodes are the most important. Eigenvector centrality, for example, doesn't just count connections, but gives it more weight to being connected to other well-connected nodes. That's how Google's original PageRank algorithm worked. It ranked websites not just by their popularity, but by the quality of who linked to these websites. Classical mechanics. Classical mechanics studies motion and forces in systems that obey Newton's laws. It's a large area of study and works for a range of topics, from planetary motion to robotics. Though classical mechanics uses many methods, an interesting one is the Lagrangian approach. Basically, if you wanted to model a swinging pendulum, you wouldn't need to sum up torques. You just write down its energy, and the Lagrangian gives you the equation of motion. Dynamical systems. Dynamical systems study how states evolve over time under rules which are deterministic and delves into many concepts. But it especially focuses on behavior which is constrained by time, especially when explicit solutions are unavailable.
Bifurcation theory. Bifurcation theory studies how a system's behavior can suddenly change when a parameter crosses a critical value. A bifurcation occurs when small changes in input lead to sudden changes in structure, like transitioning from stability to oscillation or chaos. A classic example is a straight beam that buckles when compressed. Below a certain force, it stays straight. Go just beyond that, and it suddenly bends left or right. Two new stable states emerge. That's called a pitchfork bifurcation. Symmetry in applied mathematics. This field looks at how invariance under transformations, in other words, rotations, reflections, or translations, affect mathematical models and their solutions. An example is the Taylor-Quitt apparatus. The initially symmetric circular flow becomes unstable and gives rise to a pattern of vortices. This is a classic example of symmetry breaking. Quantum mechanics. Quantum mechanics models physical systems at atomic and subatomic scales, where classical mechanics fails us. It replaces deterministic trajectories, as is explained by classical mechanics, with wave functions and operators, led by equations like Schrödinger's equation. Random matrix theory. The area studies matrices with entries which are chosen at random, and focuses on the statistical properties of their eigenvalues and eigenvectors. It was actually initially developed in nuclear physics, when physicists noticed that energy levels of heavy atomic nuclei did not follow simple patterns. Their statistical behavior actually matched the eigenvalues of large random matrices. So instead of tracking particles individually, the theory models the whole system's uncertainty through randomness. Kinetic theory. Kinetic theory describes the statistical behavior of systems that have a large number of particles, like gases or plasmas. but it can even be applied in the study of traffic flows, for example. Classically, it links microscopic particle motion to macroscopic quantities, like pressure and temperature, through equations like the Boltzmann equation. Continuum mechanics. Continuum mechanics treats materials as a continuous media and ignores their atomic structure. It describes deformation, flow, stress, and so on. It includes a sub-branch called Mechanics of Solids, which studies how solid materials deform and respond to forces.
Pattern formation. Pattern formation studies, you guessed it, pattern formation. More rigorously speaking, it looks at how complex, ordered structures spontaneously merge in systems which are spatially extended. It examines mechanisms behind stripes, spirals, and spots, as well as waves seen in nature and in experiments. Fluid dynamics. Fluid dynamics is a study of how liquids and gases move under the influence of forces. Navier-Stokes equations are at the heart of the area, which describe how velocity and pressure evolve in a moving fluid and are based on Newton's laws. Fluid dynamics models weather, ocean currents, blood flow, aerodynamics, and much more. If you're enjoying this video, don't forget to like it and to subscribe to the channel. And don't forget to tell us which area is your favorite. Magnetohydrodynamics. Also known as MHD, it's a subfield of fluid dynamics, but it studies the behavior of electrically conducting fluids, like plasmas, liquid metals, and salt water, when interacting with magnetic fields. Earth system dynamics. This area models and studies how components of the Earth system interact, like the atmosphere, oceans, land, ice, the biosphere, etc., over a wide range of spatial and temporal scales. Effective medium theories. Effective medium theories look at the macroscopic behavior of materials that are heterogeneous, like porous materials, by homogenizing, or in normal words, averaging, their microscopic structures. So generally speaking, the goal of effective medium theories is to replace a complex and microstructured material with one that's simpler, but that behaves the same way at large scales. Soft matter. Soft matter are materials that are easily deformed by external forces, like liquids, polymers, foams, gels, biological tissues, etc. These soft things show complex behavior, like viscoelasticity, self-organization, or phase transitions. Control theory. Control theory is interested in the influence of the behavior of dynamical systems through inputs, and aims to achieve desired outcomes, like stability or optimization, for example.
Signal processing. The name says it all. Signal processing analyzes, transforms, and interprets signals, which are functions that represent time or space-dependent data, like audio, images, or sensors. It might sound straightforward, but it is actually harder than it sounds. In order to have constructed this image of the black hole, astronomers had to collect and organize noisy, incomplete data from different detectors, combine it over a period of almost 2 years, and turn it into this picture. Information theory. Information theory studies the quantification, storage, and transmission of information. Basically, everything about how information works and its transmission. Applied combinatorics and graph theory. Applied combinatorics and graph theory study discrete structures and relationships, like arrangements, selections, and networks. It includes a branch called combinatorial optimization, which looks for the best solution from a finite set of discrete possibilities. It focuses on problems like shortest paths and optimal scheduling. Algebraic geometry. Though this is traditionally more of a pure mathematics field, it becomes applied through tools like Grobner bases, which let you systematically simplify systems of polynomial equations. They are used in robotics and kinematics to figure out possible positions or movements. General relativity and cosmology. General relativity and cosmology study the large-scale structure and dynamics of the universe. This is done through Einstein's field equations, which relate space-time geometry to matter and energy. The theory predicts phenomena like black holes, gravitational waves, and the expansion of the universe.
It's impossible to map all the areas, but hopefully this gave you a good idea of what the areas of applied mathematics are. This video was based on the Princeton Companion to Applied Mathematics, link in the description. If you like this video, I'm sure you're going to love this one. See you guys there.